Okay. Hey, I hope you're doing well. I didn't get to go outside today, but is spike ball still going on?
Yeah.
Okay. And then, I must have missed something.
So is the test, is it just like on the vocab words on the
Well, I happened to mention that there are a lot of words on here, but that's not just on vocab. So some of the parts are vocab word, that's for sure. We also talked about, remember when we were doing Hooke's Law? And I got into talking about direct proportionalities and inverse proportionalities. So I would have something like that. I might give you an equation you've never seen before and ask you the same idea. You know, like that's directly proportional. If that gets 5 times bigger, that would get 5 times bigger. What would this? What if it's inversely proportional? Remember that? And we did that for a couple days. So if inversely proportional, if this gets 5 times bigger, that would get 5 times smaller. That's on there. We also have on the videos you saw, we'd have some questions about, remember how you saw things about arches and stuff like that, and cantilevers.
We have to know each one.
And that was also in there. And like I said, the last part is right here on scaling, which is the last 3 pages of the chapter. But I think it actually presents the most interesting part. I like all of the parts of the chapter. This is very interesting. You're second.
So, just to clarify, we're doing 1 through 50.
Yeah, now I told you last week you need to get started on those, but if you haven't started on them, I actually will finish this in about half an hour, and we can actually, if you want, we can go over some of the questions. I can go around the room and see if you can answer the questions. We should have about maybe 20 minutes to do that. All right.
On the test tomorrow, will there be calibers and the big sticks?
No, This is pretty much, we're on chapter 18 right now, and then the next one will be chapter 19, next one will be chapter 20. So unless I have it on a handout sheet or you see it on a video, that's pretty much, it's going to stay right into there. Yeah, that's a good question. All right, well, this actually, this thing called scaling, I don't think Galileo called it scaling, but when he was studying, he figured out, he says, when you start making things bigger and trying to keep them to scale, things don't work like you think. Hey, let's make a ship. Look at this ship. What a great ship. It's only this big. All we have to do is make a bigger version of it, and it'll float just as well as this one. And then it didn't. And there were all kinds of things that were happening where you build a little model bridge, and you say, well, okay, let's just scale it up and make everything 100 times bigger. And then they have problems. So if you become an engineer, this would be really classic for you. You would not forget this lesson here. So scaling is, it says here, it's a relationship between weight, strength, and surface area as things either get bigger or smaller. So what I'm going to do is, I think we started this yesterday, is let your mind allow them to get into the world of ratios. Remember I told you a lot of the good things in physics are ratio things anyway? So, so here we go. If we look at a cube, and the cube gets bigger and bigger and bigger, so what problems could you possibly have there? All right, is everybody ready? If you're ready, I can show you this, and then I'll show you the applications of this. You'll say, wow, I never thought about that. Oh, I never thought about that either. All right, in the one-dimensional world, what's the length of that cube? It's 1 centimeter, right? And if I go to here, then I've made that 2 over 1. I've made it 2 times bigger in the one-dimensional world, 3 times bigger, 4 times bigger. All right, that's pretty easy, right? All right, question is, if you make the one-dimensional world 2 times bigger, what happens to the cross-sectional area? Now, Galileo figured out even back then in the 1600s that the cross-sectional area of a piece of wood or a piece of bone, that has everything to do with strength. The more cross-sectional area, the bigger the stronger that thing was going to be. Now, so what is the cross-sectional area of this? Of course, the cross-sectional area would actually be the same as the area right here, wouldn't it? I can cut that in half and get a cross-section, but it's the same as this. So the area would be 1 centimeter times 1 centimeter, also known as 1 square centimeter, right? So what is the cross-sectional area of this bigger cube? See that? Okay, so one more time, here we go. In the one-dimensional world, things got 2 times bigger. So I scaled it up by a factor of 2. But what happens to the cross-sectional area? It got 4 times bigger, didn't it? Let's go from 1 all the way to 4. Let's try that. As the one-dimensional world got how many times bigger? The one-dimensional world got how many times bigger? What's 4 divided by 1? 4 times bigger. What happened to the cross-sectional area? It went from 1 to what? Yes, 16 times bigger. Is everybody with me? What if I made a cube that was 5, length of 5? How many times greater would the cross-sectional area be there? It'd be the square of that, wouldn't it? So whatever is happening in the one-dimensional world in centimeters, what happens to square centimeters? What happens to the cross-sectional area? It gets that many times squared, isn't it? Now, I want you to think about this. The book doesn't talk about this. I am. Let's say I have paint, and I want to paint this. Let's say I want to paint it gold on the outside, and I want to paint this one gold on the outside. How much more will it cost me to paint this one than that one? What do you think? What do you think? So what we're going to do is paint has to do with total surface area, right? But total surface area. And so what would happen is the total surface area of this, everybody know how much that would be? It'd be one of those, plus another one, plus another one. Everybody know how many sides a cube has? Every time you roll a dice, 1, 2, 3, 4, 5, 6, right? So what's the total surface area here? It'd be 6 times that, wouldn't it? What's the total surface area here? It'd be 6 times that, wouldn't it? Okay, now all I'm trying to tell you is you can do this in your head, or you can just say to yourself this. If the one-dimensional world gets 2 times bigger, anything, cross-sectional area, total surface area, any kind of area gets how many times bigger? Not 2, but what? 2 squared. So if I go from here to here, then the one-dimensional world got 4 times bigger. The cross-sectional area will get how many times bigger? Everybody in the room should know. 4 squared, 16, right? What about the total surface area? They didn't even ask about the total surface area, but how many times bigger? I said area, didn't I? It's 4 squared. That's what's neat about this, is if the one-dimensional world gets x times bigger, then anything in the two-dimensional world is going to get x squared times bigger, like that. Yes?
I heard somewhere there's an equation that the area increases by the square of the length. Is that basically what we're doing?
Say it again.
The area of a shape increases by the square of the length. For squares.
Would you say area of a square?
Yeah.
Of course, because the area of a square would be length squared. Now, so you could think of that way. If you made had a square, it had a certain length, and you say, here's my area. What if the square was 3 times bigger? What if each length was 3 times bigger? Then that area would be 3 squared times bigger, 9, like that. Now, so what we have here, now I want to jump to the next one. In the one-dimensional world, things get either 2 or 3 or 4 times bigger, and the two-dimensional world called area gets how many times again? 4, 9, 16. The square of that, right? Now, let's go to the third-dimensional world, 3-dimensional world called volume. Now, what's the volume of this cube? It's 1 times 1 times 1. It's 1 cubic centimeter. What's the volume of this guy? 2 times 2 times 2, 8, isn't it? Ah, interesting. As the one-dimensional world gets 2 times bigger, what happens to the 3-dimensional world? It went from 1 to 8. How many times bigger is that? 8. Okay, let's try it now. I'll try it again. As the one-dimensional world gets 3 times bigger, what happens to the three-dimensional world of volume? It went from 1 to what? 27. You see a pattern yet? As the one-dimensional world got 4 times bigger, the three-dimensional world went from 1 to 64. You see a pattern? If the one-dimensional world gets 5 times bigger, the two-dimensional world of area gets 5 squared times bigger, but the three-dimensional world gets what? 5 cubed times bigger. Now, that is something, now, let's put this together now. Let's put this together and say, what was Galileo trying to say was going to happen? All right, how does scaling affect strength? All right. So, you've got a piece of wood, for example, and let's say you have, it looks like that, and then you said, you know what, I'm going to make the one-dimensional world, instead of x, it's going to be twice as long. Instead of this long, each side is going to be twice as long. Do you think that second piece of wood is going to be stronger? Okay, but he said the strength comes from the cross-sectional area. In the one-dimensional world, this got how many times bigger? Do you want me to use regular numbers? Okay, how about 1 and 2? As in the one-dimensional world, it got 2 times bigger, didn't it? What happens to cross-sectional area? Not 2 times, but 4. It should be 4 times stronger. They said that the strength came from the cross-sectional area. I have 4 times the cross-sectional area used to be. So that is definitely a stronger piece of wood, isn't it? Does that make sense to you? If I had a piece of wood like this, and you stood on it and said, whoa, looks like it's gonna break. And then I'd give you stand on this, you said, no, that's not gonna break. So what's the problem? What's the problem with a bone that has a certain cross-sectional area and another bone that has twice the cross-sectional area? That bone's gonna be stronger. The second bone is gonna be stronger, so what's the problem? Yes?
The volume goes up by a factor of 3. Like also-
Yes, yes, yes. Now, if you're a human, and let's say we want to take a human and scale up the human scale factor of 2. Everything about you that's one-dimensional, I'm going to make it twice bigger. The thickness of your bone, I'll make it twice as thick. Your bones will be 4 times stronger. Got it? So your bones, the cross-sectional area, your bones will be 4 times stronger. That's good news. That's good news. But what happens to your volume? What happens to the human's volume? Remember, that's a 3-dimensional world. The volume won't get 2 times bigger. It won't get 2 squared times bigger. It'll get what? 2 cubed. So if you were a regular human and you had, your bones had a certain kind of cross-sectional area, and you had a certain volume, and you said, I'm a regular human, and I seem to be able to handle my own weight. But then, what happens if you make scale it up by a fact? Let's take a number, okay? Let's make a number. Let's say this is 16, and this is I'm just making up a number. No, wait, let's do it easier. Let's say the one-dimensional world is 1, and this will become 2, and this will become 2 cubed. That'll be 8. See that? All right, so if you're a regular human, you have your bone strength is big enough to handle that much volume, okay? But what happens then if I double the the regular one-dimensional world? This gets 4 times bigger, and I'm sorry, this gets, whoops, I made a mistake. Wait, 2.
16.
Sorry, my fault. Let's try again. The one-dimensional is 1, cross-sectional area would be 1, and the volume would be 1. Okay? So I've got some numbers here. But what if I made this 2 times bigger? That'd be 2, and this would be what? 4, it'd be the square of that, wouldn't it? And then the cube would be 8. Now you used to have this ratio. How much volume it has. Matter of fact, where is my weight? Where is my weight? It's in my volume, isn't it? I didn't say weight was equal to volume, but where is my weight? It's in the 3-dimensional world. So if this gets 2 times bigger, This gets bigger. That's 2 squared times bigger, 2 cubed times bigger. But what happened to my ratio? I used to have a 1-to-1 ratio. Now what is it? 2-to-1. So I'm gonna have trouble handling that. Let's do it again. Jump one more. Let's do that. That's 3 times bigger. That's gonna be at 9 times bigger. And what's this gonna be? 27 times bigger. That's 3 cubed. So I went from a nice ratio to that's not so good to what now? Now I'm asking my bones, which are much stronger, to handle 3 times. I have to have a 27 and 9. I'm asking it to support a huge amount more weight. And that's why you really can't have big animals. You can't have a big ant or a big King Kong. You can't do that because their bones are getting stronger as you scale them up, but their weight, and you're right, the 3-dimensional world gets bigger faster than the 2-dimensional world. You cannot keep up with it. All right, so let's go down here and see what it said down here. What are some applications of that? And I think these are kind of neat. What if you had a house and you love this house? It's a small house and you love it. And then you got to work a lot and you made more money and you said, I love that house so much, it's just not big enough for me. What I'd like to do is scale the house up 3 times. My little house, which used to have a length of this much and a width of that much and a height of this much, all those are going to increase by 3 times. So I build my new house. The question is, how much more paint would it take to paint my new house than it did my old house? You got to stay with me on this, okay? So I must scale it up 3 times, right? The 1-dimensional world got 3 times bigger. Where does paint go? On the what? On the surface area. That's the 2-dimensional world, isn't it? So if I scale my house up by a factor of 3 in the 1-dimensional world, then how much more paint am I going to need? Not 3, but what? 9. And believe it or not, you may not like it. It's going to take me 9 times more paint to paint my new house. I want to put a roof on a new house. How many more shingles? How much more shingles would I need than I did for my little house? Where do shingles go? On the area. So how many times more shingles then? 9 times more shingles. I need carpeting. How much more carpeting will I need than I did for the small house? 9. Carpeting's in 5. But then, this was going to shock you. What about my heating and air conditioning bill? I pay this much a month for my little house. How much will my heating and air conditioning bill go? 27 times more. People are always shocked when they add a room to their house, like a 12 by 12 room. I'm going to add a new part to my house. They are shocked when they get their next utility bill. Because what part of the house is getting heating and air conditioning? The what? Starts with a V? The volume. And the volume is going to be 20, not 3 squared, but 3 cubed, 27 times more. People get shocked when they add. Has everybody done that in their house? You probably don't talk to your parents about how much they pay for utilities or anything like that, do they? All right, we have another one here. It said, what if I gave you 10 pounds of big potatoes and 10 pounds of little potatoes? And I don't want to peel them. I'll take a peeler. And which pile of peels are going to be bigger? Which pile of potato peelings will be bigger? The peelings from the 10 pounds of big potatoes, or the peelings of the 10 pounds of little potatoes, or will the piles be kind of the same? What do you think? How many people say the piles will be the same? How many people said the big potatoes will have the bigger pile of peeling? How many people say the little potatoes will have the biggest pile? So, I want to show you how this works, okay? When you're small, this is a key. Small things always have the most have the most surface area per volume. Per volume. As they grow, you get more surface area, but who grows faster than that? Volume grows faster than that. So a small potato will always have more peelings per pound than a big one. So the 10 pounds of small potatoes, those peels would be bigger. You'd have more peeling there. They ask the same question here. Which one would cool a glass off faster? 1 pound of ice cubes or 1 pound of crushed ice? Which one will cool the water off faster? Crushed ice is small. It has more what? More surface area per volume. Now, in this case, there's more area for heat to go in per second. So crushed ice always cools it off faster than an ice cube. Anytime, let's do this. 1 big chunk of iron, 1 kilogram of iron, hot iron. Another kilogram of hot iron cut into 100 cubes. You lay them out, let them all cool. Who cools faster?
With more surface.
The one that has more surface area per volume. The 100 little cubes will cool much faster. That's why you do that. That's why you can cut hot things up. You can cut them up and get more surface area. They'll cool off faster. Now, here's something you're not going to like, but it's true. I guess you'll like it. Let's say you have a baby. Not now, but later. Let's say you have a baby, and somebody says, "Well, the baby might be getting cold." And you say to yourself, "No, I'm not cold. I'm not cold. Why would the baby feel cold? I don't feel cold." See, you forgot your physics lesson. A little baby has what? He has more surface area per volume than you do, so he's losing more heat per second than you are. You might feel great, but that baby could definitely be cooling off really fast. That's why they keep babies covered up, even if you don't feel cold. Are you with me? Okay, this is some good stuff. What would happen? They had a great picture in here. They had a mouse, and they talked about a mouse and elephant, didn't they? Now, I'm not trying to trick you, okay?
Being tricked.
Who has more surface area, a mouse or an elephant? Are you kidding me? An elephant. Elephant has a huge surface area. But which animal has more surface area per volume? Now, so here's what happens. A warm-blooded animal that's small has a huge surface area to volume, and it cools off incredibly fast. Now, if you don't want to die, you better keep burning fuel. What if I run out of fuel? I better go get some. So they have to eat a lot. They eat a lot. Mice eat all the time. They have to eat a lot because they're cooling off very fast. Now, the other thing can happen, and an elephant is so big, it has so much surface area, but it does not have a huge amount of surface area per volume. And so big animals have trouble, not because they're going to get too cold, because they're going to heat up. They're going to heat up too fast. Animals like elephants have a lot of trouble in the heat, a lot, because they already can't get rid of enough heat. So that's why you see them going into the water or into mud, which contains water, and that will help them to lose heat. And in the book talked about these elephants with their really big ears. And what do flat things have a lot of? They have a lot of what? Surface area per volume. And so what happens is you run blood through those ears and you lose lots and lots of heat per second. And they say that's what helps elephants to cool off. Yes? Have you read that? Okay. What was the other thing they had? Let's see something else. Oh, yeah. I want to show you about cells. And that'll be it. Does everybody understand how that works, that scaling thing? So let's try humans again. Let's say you had a human and you want to scale him up by a factor of 3. Let's make the human 3 times, scaled up 3 times. So every one-dimensional unit is 3 times bigger, okay? 3 times wider, whatever. Everything's 3 times bigger. So you're going to make this big human. Will the bones of that new human be stronger than the original human?
Yes.
How many times stronger?
9.
Yes, 3 squared, right? Because that's cross-sectional area.
Yeah.
But how much will the new human weigh? His bones are 9 times stronger, but you're asking him the 9 times stronger bones to support 27 times, and that human will actually be less strong. He'll be weaker. As a matter of fact, it might collapse. His legs will break, maybe. That's why you can't have big humans. Now, let's go the other way. I always like some of those science fiction movies where they shrink humans, you know. So let's shrink a human. Let's shrink a human. Reduce it by 10. Let's say 10, okay? And so we got a human. Let's make a scale factor of 10 lower. All right. Oh, bad news. The bone strength's going to be not 10 times less, but 100 times less. Wow, the bones can only handle about 1/100th of the weight. Good news, the human only weighs how much? 1,000. So now the little human now is actually 10 times stronger per pound than this human. If I kept shrinking a little bit, you might be like an ant. You might get to the point where you could lift 50 times or 100 times your own weight. I can't do that now.
But Amy.
Now remember, I didn't say stronger, but stronger for their weight. You get that? So humans could be stronger for their weight if you scale them down. But if you scale them up, chances are they would have trouble even standing up without breaking their bones. All right.
Yeah.
Well, let me show you the last part of the lesson here. And you see if this makes sense to you. If you happen to have a calculator,
What's that? I don't want to mess my brain.
this was on the handout sheet I gave you. So I'd like you to take a look at this one. And I'll do this for about 5 minutes or so, and then we're going to head and try to answer a lot of the questions in the book. All right, stay with me. I used to teach biology, and this is actually a lesson that they have in most biology books. But because you're 9th graders, and you thought like 9th graders, most people in 9th grade did not understand this lesson at all. I bet if I went over there next door and got that biology book, I bet this lesson's in there, but you may not even remember it because it was just something about numbers and it didn't make sense to you. Are whales big because they have big cells? Are ants small because they're made of small cells? That's a great question, and they wanted to answer that, and they did answer that question. On the average, most cells are about the same size. Now, I will tell you there are exceptions. Some exceptions are incredibly thin, long cells. And I'll tell you why that's an exception later, okay? But right now, whales aren't big because they're made of big cells. And I used to always enjoy having the kids do things with the microscopes when I taught biology. And I would always get pond water and try to reproduce a lot of the microorganisms there, the protozoans. And some of those are really like I don't know, monsters. Some of those little one-cell things are like unbelievable. They're predators and things like that. And I always thought that was fascinating how many different one-celled organisms there were. But then ask yourself this question. Why don't I see big versions of that? Why couldn't they have a big version of a paramecium? And you never do see it. And that's the question. Why is it the cells seem to be about the same size? So here we go. I'm not telling you the cells are like spheres. There are some that are kind of roundish. But they use this, instead of using a cube, they're going to use this. Now, do you see this cell here has a radius of 1, whatever you want to call it, 1, whatever. A radius of 2, a radius of 3. Now, what are you doing when you go from here to here? In the world of ratios, the radius got what? It went from 1 to 2. The radius of the cell got what? 2 times bigger. What if you go from here to here? The radius went from 3 to 1, or 1 to 3. It got 3 times bigger, didn't it? Are you with me? All right, this cell is growing. We're going to let this cell grow. Okay, let's see what happens. The surface area of a sphere is 4 pi r squared. Now, if I plug that number in there, 4 pi r squared, if I plug that in there, you'll find out that the surface area of the little cell is a number like 12.6. Yes, okay. Now, what is the surface area of a cell whose radius is twice as big? You plug that in, and you get 50.3. Now, with your calculators, take the big number and divide it by the small number. In the one-dimensional world, the radius got 2 times bigger. What happened to this surface area? What'd you get? What's 50.3 divided by 12.6? Uh-oh. What is it? It's about 4, isn't it? Is that right? Now let's go to the other one. Let's go from here all the way down to here. If the one-dimensional cell gets 3 times bigger, what happened to the cross-sectional area? It went from 12.6 all the way to 113.1. How many times bigger is that? You take 113 divided by 12.6. What do you get? Something close to 9. Is that correct? Now watch. See if this makes sense to you. If the one-dimensional world got 2 times bigger, the area, the two-dimensional world, got how many times bigger? I'm looking at your faces. I can't tell. If the one-dimensional world got 2 times bigger, the two-dimensional world got how many times bigger? Which is 2 squared, isn't it? And the one-dimensional world got 3 times bigger. What happened to the two-dimensional world of area? It got how many? 9. That's 3 squared, isn't it? Now let's go over here. Let's find the volume. The volume of a sphere is 4/3 pi r cubed. If you plug that number in, 1, then you'll get a volume of 4.2. Okay, fine. The little cell has a volume of 4.2. What if the cell got twice as big in the one-dimensional world? Use your calculators. What is 33.5 divided by 4.2? How much?
7.97.
Okay, 7.97. Oh, okay, 7.97. Okay, that's 8. Okay, sorry. So, so what happens in the one-dimensional world? You got 2 times bigger. The two-dimensional world got 2 squared times bigger. The three-dimensional world got 2 cubed times bigger. Let's do the next one. Let's go from here all the way down to here. It went from a volume of 4.2 to a volume of 113.1. Okay, how many times bigger did that get? All you do is take your calculator, 113.1 divided by 4.2. How much? So about 27, right? Does that make sense to you? And I want to show you why scientists think cells don't keep growing and growing and growing. Here's why they think. What is the surface area to volume ratio? All right, look now, take your calculators. Here's what they did. Surface area to volume. Surface area to volume. Surface area and the little cell. Hey, I got plenty. I got plenty of surface area per volume. I have 3. 3 to 1, right? I got plenty of surface area. What happens when the cell grows? What's the surface area to volume ratio now? Whoa, now it's only 1.5. And now let it grow again, and what happens? So what happens to the surface area to volume ratio when things grow? Does it get bigger or smaller or stay the same? Smaller. Why is that a problem with cells? Here's what cells do. Ready? Ninth grade. The cell membrane allows certain things in, allows certain things out. I need oxygen in. I need food to come in. I need waste products to go out. Everybody get it? When you're small, you got, and where's all the chemistry going on? What part of the cell is chemistry going on? In the cell membrane? Where's the chemistry going on in the cell? I'll give you a clue. It's the insides, the volume, right? The volume of the cytoplasm, isn't it? So the chemistry is taking place in the volume. When you're a little cell, all this volume says, oh, I got a lot of demands. I need oxygen. I need food. And here's some waste products. Get rid of that. That's okay when you're small. You got plenty of surface area to volume. And we're going to be okay. So guess what we're going to do? We're going to grow. How you doing down there, surface area? Oh, no, not bad. But you know what's happening as we grow, you're getting bigger than me faster. And so the ratio of surface area to volume is kind of shrinking, and I'm having a little bit more trouble keeping up with your demands. You demand a lot more oxygen now, and you're producing a lot more waste products, but I guess I'm okay. And then your cell starts growing, and it's going to get to the point, here's what happens. It gets to the point where if the cell gets any bigger, it will not have enough surface area to volume to keep it alive. It won't have enough surface area to bring in enough oxygen and food. You won't have enough surface area to get rid of your waste products. And here's one choice. You keep growing and you're going to die, or you can do something kind of unusual. And this is what biologists think happens. That sets off a little trigger in the cell. And when they get a crucial point where there's almost not enough surface area to volume ratio, the cell starts dividing. And when it divides, it turns itself into two smaller cells, which has enough surface area to volume ratio, and then they will grow, and then they will divide, and then they will grow, and that's why they believe the cells are about the same size. Yeah, if there were some big parameciums, I'd open up a pet store right now. You know, I get a paramecium this big, a one-celled organism. People, they eat that up, all right? Put them in your aquarium, and okay. But we don't have those. The only exceptions that I know of are cells that have incredibly thin and long. You do have some nerve cells that might be this long, and yet they're really small. What do flat things have a lot of, though, anyway? A lot of surface area per volume. And that's the only time you're going to see cells that might be bigger, they might be longer than cells. The other thing that God said, he can do this. Every once in a while you'll see a cell that might have all kinds of convolutions there. What do you know about a cell like that? It has a lot of what? It has a lot of surface area per volume. Remember sometime in elementary school he said, if you took the coastline of Sweden and straightened it out, it'd go around the world 2 times. What? Because the coastline of Sweden goes, right? What do we find in your intestines? What can you do? A lot of surface area to volume like that. Even if I take this under a microscope, guess what I see in the intestines under the microscope? The intestines needs a lot of surface area per volume. You take in a lot of nourishment like that. One more. In the cell, do you remember this saying, an organelle that looked like this? And it was called the powerhouse of the cell? Mitochondria. The inner membrane of mitochondria. Infolded. What's going on there? Remember that, you called it, okay, did you call it cellular respiration? What did you call it? Is that what you called it? Okay, so this is where ATPs are made, right? And so a lot of chemistry is going on there, and by having infolding for the same amount of size, you can get a lot of surface area. Okay, well, I hope you liked it. That lesson is pretty neat. It also tells me why will I probably not find big bears at the equator. What do bears have trouble with at the equator? Heat. They would cook themselves. But what are you not going to find in the Arctic? Thin little animals like deer. No, you're not going to find thin little animals like deer. They would lose heat so quickly, they would die. So that's kind of interesting how animals find themselves, depending on their surface area to volume ratio. That's where you actually find them. Okay, let's see. I think that's about it. Yes?
So some evolutionists believe that humans have been getting like better. Is that argued?
Well, that's a great question. If you're an evolution type person, you would say, well, we have evidence from the human skeletons over time that humans in certain countries, most countries, they're bigger than they used to be. Doorways are bigger than they used to be. And that's a great question. Now, do I think that all environments would favor a bigger human? I don't. I think there would be some environments where a small human might be able to escape through the woods or might be able to do something that big ones couldn't. I also think that big humans might have more trouble in a hot climate. On the other hand, I might think a bigger human in a colder climate might have a little advantage. So I think because we have different environments on the Earth, we could also say you wouldn't necessarily have to have. I think what's happening is there's better nutrition. The access to food and medicine is so much better now that lots more people are surviving, including the tall people, including the small. So that's a great question. What happened back then? Did the tall people die for some other reason, or there weren't too many tall people? That's a great. That would be a great thing to research that.
Does that mean that people would also have to be getting like thinner?
Here's what's happening in the United States. The United States, we're getting bigger and taller and bigger. And so we have a lot of people that are obese. And if you go to other countries, you don't see as much of that. And that does have a lot to do with the diet and the kind of foods that we eat. Now, will that have an effect on different things? I think so. If you're kind of a bigger person and it's hot out, you're going to have a lot of trouble keeping cool. And yet, if I was a smaller person, I wouldn't have as much trouble. Now, in the winter, a small, thin person, they are going to have trouble. They're going to be cold a lot. And so they need to have either more clothing or get it where it's warm. All right, these are great questions. Now, yeah, go ahead. Yeah. Okay, what I'd like to do the rest of the period is let's take a look at 1 through 20. 1 through 20, see if there are some questions there. Let's do some of those real quickly. Ready, number one? How does the arrangement of atoms differ in a crystalline than a non-crystalline substance? Do you have a good answer for that one yet?
Wait, what?
Yes?
Crystalline substances have a standard pattern that repeats
It's
the entire substance.
Okay, a non-crystalline might have little pockets, okay? All right, number two, what evidence do we have for the microscopic crystal nature of some solids? Yes?
X-ray imaging.
Yeah, X-ray, usually they'll shoot X-ray diffraction at it, imaging, yes. Number three, what evidence do we have for the visible crystal nature in some solids?
Like diffraction.
You mean like that? Okay. We can look at it, can't we?
You can see the crystal.
Yeah, you say you see it. Okay, next. What happens to the density of a uniform piece of wood when you cut it in half?
It
Stays the same.
stays the same.
Yes, it does. Because the volume gets cut in half, but so does the mass, and the ratio stays the same. Are you starting to think a little bit more in ratios? That's usually what keeps some people from going into science and engineering. All right, just make yourself get in that world. Next, uranium is the heaviest atom found in nature. Why is uranium metal the most dense? That's a tough question to answer. Do you have an answer for that?
Because uranium as a metal, the atoms are spaced farther apart than other substances.
Well, we actually have, if you go here to osmium, iridium, platinum, gold, that four in a row, they are actually the four most dense materials that we know of. So they're all metals. So metals do like to pack them close. It's just that I don't think the book gets into why. It's the not only the number of protons in a nucleus, but the number of electrons. That combination allows some things to get closer than others. I don't think the book, that's my opinion, I don't think the book mentioned that very much. Okay, let's go to 6. Which has a greater density, a heavy bar of pure gold or a pure gold ring?
Same.
Okay, so now you're catching on there. Does the mass of a loaf of bread change when you squeeze it? Even though we call it bread, it's actually bread and air, isn't it? So when you squeeze a loaf of bread, the volume goes down, and
Wait, what?
does it get more dense or less dense?
More.
It gets more dense, okay? 'Cause you're actually squeezing the air out of it too. Does its volume change? Yes. It gets smaller. Does the density change? Yes, it gets greater. What's the difference between mass density and weight density? You know, mass density is grams per cubic centimeter, and I bet there's some engineers that still use weight, like pounds per cubic centimeter, and that's the only difference. Weight is weight, density is weight per volume. Let's go next. What is the evidence for claim that steel is elastic?
Oh,
Yes,
Steel will return to its original state.
a little bit louder.
for extended time.
Say it again.
Steel will return to its original state.
stand up, please.
Right.
And after it's been formed.
And we see a lot of springs that are made out of steel. Okay, next, what's your evidence to claim that putty is inelastic?
Oh.
Okay.
It doesn't return to, after being altered, it doesn't return to.
All right, next, what is Hooke's law? Yes,
Stretch is proportional
what is?
to the stretch.
Yes, the amount of stretching is directly proportional.
To the force.
Yes, okay. Next, what is the elastic limit? Yes.
How far can you stretch before it stays like that?
Lazy like that.
Right. If you apply a force and it goes back to its original shape, you have not reached the elastic limit. If you apply a force even to a spring and it does not go back to its original shape, you've exceeded the elastic limit. Let's go to the next one. A 2 kilogram mass stretches a spring 3 centimeters. How far does the spring stretch when it supports 6 kilograms?
No.
And again, it's assuming you didn't reach the elastic limit.
9.
And even though its mass is 3 times bigger, is that correct? Its weight is also 3 times bigger, and weight's a force, isn't it? So the force is 3 times greater. So the stretch has got to be
9.
3 times greater than 3. That's 9. Yes. Is the steel beam slightly shorter when it stands vertically?
Yes.
All right, not a lot, but because there's only a little bit of compression, but a little bit, right?
Yes.
A little bit.
But there's
Next, where is the neutral layer in a horizontal beam?
in the middle.
Okay, excellent. Why is the cross section of a metal beam eye-shaped and not rectangular?
The sides aren't even the strength. Where it is locked in metal, it's not.
Only the top and bottom.
The top and bottom needs more metal because that's where the most compression and tension takes place, and the neutral area doesn't need as much metal. There's not much stress there. Let's go down. What is the weight to strength relationship in scaling? As things are scaled up, go ahead.
I said as the size increases, it grows heavier the faster and it grows stronger.
What does? As things increase their size, their bones do get stronger and the weight gets bigger. But what about the weight to strength ratio?
The weight used.
You become weaker or stronger as you grow up, as you get bigger? You actually get weaker for your body weight, doesn't you? Okay, if the linear dimension, that's one-dimensional world, are doubled, how much does the total area increase? 2 squared, wouldn't it be? 4 times, yes. Ready? How much does the volume increase?
8. Yeah.
2 cubed, which would be 8, yes. True or false? As the volume of an object increases, its surface area also increases, but the ratio of surface area to volume decreases.
It has true. Dang it.
all controversial.
Well, let's do part of it. Does the surface area increase?
I don't know this.
Yeah, a bigger ball has, all right, but what about the surface area to ratio? Small things always have the most surface area to volume ratio. You get that? If it gets bigger, the surface area to volume ratio gets smaller. You have more surface area, but not more surface area per volume. Volume gets bigger faster than surface area. Which will cool off a drink faster, 10 grams of ice cubes or 10 grams of crushed ice?
Crushed ice.
Okay. Which has more skin, an elephant or a mouse?
Mouse. Wait, no, Elvin. I'm it, Elvin.
Okay, which one has more skin per unit of body weight?
Mouse.
Okay.
Yeah, that's what I thought.
All right. Keep on going a little bit. You take 1,000 milligrams of vitamin. Your friend takes 1 gram of the same vitamin. Who takes more?
Same.
Okay.
Except for-
Your friend says that the primary difference between a solid and liquid is the kind of atoms in a material. Do you agree to disagree? I don't know why he asked that. I don't think he spends that much time on that here. It's not just the kind of atoms, because atoms sometimes can pack themselves very close, like a
ice.
solid, and like mercury. I'm not even sure why. Mercury is right next door to the most dense metals, and yet mercury, it is dense, but not the same density, and it's actually a liquid. Yes.
Gallium's another example. It's normally a metal, but with just a tiny bit of heat, like heat your palm, it will.
Right, gallium and also cesium, same thing. Cesium would look like a solid. If I laid it in my hand in a test tube,
Well, it'll also blow.
it would turn to a liquid. Okay, let's go on. I want to do the hard question. I got less than a minute. 30. How about number 30? That's the hardest question. Okay. Consider a model steel bridge that is 1/100th the exact scale of a real bridge. If the model bridge weighs 50 newtons, what will the real bridge weigh? Oh. The model only weighs 50 newtons. Let's make the real bridge. Let's see, the one-dimensional world is going to get 100 times greater. Where is the weight? Where's the weight of a bridge? Is it found in the area or volume? It's found in the volume. So, if you got 100 times bigger in a one-dimensional world, the weight of that bridge will be what? Not 100 squared. 100 cubed. 100 cubed. What's that? 100 cubed. That's 10 to the second to the third. That's 10 to the sixth. It'll be 1,000,000 times heavier. And what's 50 times 1,000,000? 50 million. If you had, how many of you have 50 million before I told you? Okay, there we go. One more time. If the model bridge doesn't appear to sag, then is this evidence that the real bridge won't sag? No, not at all. All right, I couldn't do all the questions. I know that. There are some harder questions when you get to the think and solve problems. I'm gonna be here after school. If anybody need a little extra help, little help session, I'll be here after school. Okay. I really would like to see you.